In the current session, we will discuss in brief about another type of memory known as cache memory. In the previous two sessions, we did discuss about an important type of memory known as content addressable memory or associative memory. You know what is associative memory, its features, and how to implement the same. In the current session, we will have an idea about what is cache memory, why it is required, and what are its features. Of course, you can quickly recall in the memory hierarchy session, we have discussed about three different types of memory. You can quickly recall it, please. Auxiliary storage, that's secondary memory. Examples being tape, magnetic tape, and magnetic disk. The program and data which are permanently stored in the auxiliary storage devices gets transferred to your primary memory known as RAM. Of course, you know the speed of auxiliary storage is roughly of the order of 10 power minus 3 seconds, especially in the case of a disk. Whereas in the case of RAM or primary memory or main memory, its access time is 10 power minus 9 seconds, known as nanoseconds. If you make data available in RAM, which is directly connected to CPU, as well as instructions, the CPU's waiting time gets reduced. But over a period of time, the CPU speed has increased, whereas we are unable to match its speed with respect to the speed of your primary memory known as RAM. So the RAM speed and CPU speed both are at different levels. So there is a speed disparity. To compensate the speed difference, one more memory gets introduced that sits between your main memory and the CPU, that is called cache memory. What CPU can do? CPU, instead of accessing every time the main memory or RAM, it can access the cache memory first. If the word or data or instruction, if it is found in cache, it can get it from cache, process it, and then sends the resulting value back to the resulting value back to the cache memory, which means it need not access main memory at all. What is the advantage of this cache memory? You know pretty well. Speed is the important characteristic feature of cache memory. Of course, you did know that the speed with which the cache memory operates in the given time interval, instead of fetching one word or one data item from primary memory, in the same time interval, you'll be able to access or fetch 10 data items from cache memory. So that is the power of cache memory. When I mean power, it is referring to its speed. They are in the ratio roughly 1:10. So instead of fetching one word from primary memory, you can fetch 10 words from cache memory in the same amount of time. So that is the special feature regarding cache memory. How can you store data in cache memory? What is the other important difference? Primary memory is volatile. Cache memory is also volatile. Primary memory is made up of dynamic RAM, that is using capacitors, DRAM. Whereas when you come across cache memory, its design principle is based on static RAM. Of course, you know static RAM is made up of transistors. And static RAM is faster than dynamic RAM. You can recall the differences between static RAM and dynamic RAM here, so that you can understand the concept much better. So cache memory's advantage is its speed. Its design principle is based on static RAM and it uses transistors. Whereas dynamic RAM uses capacitors and its speed is relatively lesser than your cache memory. Okay. What about the size between the two? When I mean size, I'm talking about the memory capacity. Primary memory or your RAM is in terms of gigabytes, that is generally denoted as GB. For example, 4 GB RAM. When you come to cache memory, its memory capacity is in terms of only MB, 256 MB RAM or 256 KB cache, 256 MB cache or 128 MB cache or 64 MB cache, etc. So the size of cache memory is in MB, that is megabytes. 1024 kilobytes is equivalent to 1 megabyte. Okay. Whereas the size of your primary memory is in terms of GB, 1024 megabyte is equal to 1 gigabyte. So its memory is in GB, whereas cache memory is in terms of MB. That means whatever is stored in primary memory cannot be stored, the entire whole amount of data and instructions cannot be stored in cache memory because its capacity is less and moreover it is quite expensive. Not only faster, cache memory is not only faster than primary memory or your RAM, cache memory is also quite very expensive when compared with your primary memory, which is made up of dynamic RAM. That is DRAM, which uses capacitors. How this concept of cache memory works? It is based on the property known as locality of reference. I did mention about what is locality of reference in the beginning. Again, you can recall. So when you go in for execution of a program at a given point of time or at any given time interval, it is confined to only to a few localized memory spots. And this property is called as the locality of reference. Let me give an example. For instance, you are using a for loop. Of course, you are learning C programming, I believe. And in the case of for loop, for example, I say the loop has to be run 10,000 times. During those 10,000 times, assume the for loop has got 4 or 5 instructions, and it is going to manipulate some counter, summation counter, or let me say product counter. For 10,000 times repetition, instead of fetching the instruction from main memory, if you are able to fetch the instruction from cache memory, since cache is faster than primary memory, the CPU's waiting time gets reduced. That means over a period of time, when you are executing a for loop 10,000 times, if that for loop is made available in cache memory, it reduces the idle time or waiting time of CPU. When the waiting time of CPU gets reduced, its busy time or the performance factor gets increased, which in turn increases its throughput or performance. So that's the basic idea. Therefore, whenever you go in for execution of any program, it may follow a sequential flow in nature. Execute the first instruction. After executing the first instruction, then you go for executing the second instruction, then the third instruction, and so on and so forth. Sometimes you may come across looping structure in between. That means when you start executing the first instruction, you know pretty well the next instruction to be executed is instruction number 2. When you make the first instruction, the second instruction, third instruction, etc., in a straight line flow, if it is made available in cache memory, you are making your CPU not to refer to dynamic RAM at all. That means it need not access the RAM memory at all. Its request will be satisfied by the cache memory itself. Since cache is faster than your RAM, therefore, you are improving the CPU's performance. That's the basic idea with regard to why we make use of cache memory. And this property is referred as a locality of reference property. So let me come to one more example. Suppose in case you're having a subroutine, when you're writing a main program, you are writing a subroutine to calculate factorial of a number. You want to calculate for number of, let me say for 1,000 numbers, I have to calculate factorial value. 1,000 different factorial number. For 1,000 different numbers, I want to calculate factorial values. Therefore, what you can do, you can write a subroutine for computing factorial, and this factorial subroutine will be called, subprogram or subroutine will be called, let me say 1,000 times or 10,000 times. Within that, we'll be having a, let me say, instructions which are bound to be part of your subroutine known as factorial. All those instructions will be repeatedly executed 1,000 times or 10,000 times, depending on the need of the user. If I can make this factorial subroutine available, the entire subroutine consisting of instruction and data available inside cache memory, CPU's request will be satisfied by the cache memory itself, and you are preventing the CPU from accessing the main memory. So for what you should do judiciously, you have to transfer the subroutine from main memory to CPU so that its access to main memory gets truncated. It doesn't happen at all. That's the basic idea behind the use of cache memory. So keep in mind, it is based on the property of locality of reference. Over a period of time, CPU's requirements will be satisfied by the cache memory itself because of the property. What does it say? It is going to execute only few instructions which are part and parcel of a memory location. It is localized. That's the basic idea behind the concept of cache memory. Therefore, cache memory is faster than primary memory. Its capacity is in terms of MB. And moreover, based on the locality of reference property, you are able to satisfy the need or requirements of CPU, thereby transferring the data and instructions, which are most frequently used by the CPU from primary memory or RAM to the cache memory. And then when you come to cache memory, another important point you have to keep in mind is known as what is known as heat ratio. What is meant by hit? What is meant by miss? When the word searched by CPU or when the data required by the CPU is made available in cache memory, it is called hit. When the data is not available, it is called miss. Let us say this way. Assume your primary memory access time is 1000 nanoseconds. You know pretty well what is the access time of your cache memory. It is 100 nanoseconds because it is in the ratio 1:10. Assume the access time of cache memory is 100 nanoseconds, whereas this access time of primary memory is 1000 nanoseconds. If you calculate the ratio, it is going to be 1:10, as we discussed earlier. Now, if the data is available in cache, CPU has to spend only 100 nanoseconds to get the data item. Whereas if the data is not present in cache, CPU has to spend 1000 nanoseconds every time. That is 10 times more to get the same data item from primary memory. That is your RAM. Now, if the data item is found in cache, then it is going to be hit. If it is not found, it is called as miss. What is the hit ratio? It is the numerator is going to be total number of hits, and the denominator is going to be total number of hits plus misses. For example, when I say the hit ratio is going to be 90%, that means 90% of the time, the CPU's requirement is satisfied by the cache memory, and 10% of the times its request is not satisfied by the cache memory, and during those 10% of the times, CPU has to get the data from, let me say, which memory? Primary memory. Now you calculate the time taken. Probably I could put this way. It is going to be 90 times, 90 into 90 times, it is 90% is available. That is assuming it is going to be 90 words. Out of 100 words, 90 words are available in cache. So 90 into 100 nanoseconds, that is going to be the numerator, divided by 10% of the time it is not available. In that case, it is going to be 90 into 100 plus 10 into total time taken is 90 into 100 nanoseconds plus 10 into 1000 nanoseconds for accessing the RAM. If you calculate the average time taken, it is going to be roughly around 200 nanoseconds. So that's the basic idea behind the hit ratio, which is better. If cache is absent, the average time spent by the CPU is 1000 nanoseconds for every word or for every data. If cache is present, if you are able to maintain a hit ratio of 90%, then the average access time is brought down from 1000 nanoseconds to 200 nanoseconds. Let me say, for example, that is the essence of or the presence of cache memory. If cache memory is present, it drastically reduces the average memory access time. It brings down from 1000 nanoseconds to on an average 200 nanoseconds, assuming the hit ratio is 90%, with 100 nanoseconds for every access to cache and 1000 nanoseconds for every access to a main memory. So this is a basic idea behind the hit ratio. If you improve the hit ratio, automatically the average memory access time gets reduced. When the hit ratio is less, then CPU unnecessarily spends time on the cache memory. Since the word is not found, it has to again access the main memory to get the required data. So hit ratio must be kept on an average anywhere above 80%. So when they have analyzed from the research point of view, on an average, it is above 85%. Therefore, the presence of cache memory in any computer system, it drastically reduces its access time and thereby improving the CPU's performance. So that's the basic idea. The next important point you have to keep in mind is how do we do this transformation? For example, I said in the discussion, the data has to be transferred or instruction has to be transferred. Which data and which instruction? The data and instructions which are most frequently used should be made available in cache. So that means you have to transfer those most frequently used data and instructions from RAM to cache memory. And this is called a transformation. This is called as the mapping process. How are we going to map the data and instructions from primary memory to cache memory? So that we can see in the next session. And before that, before we close this session, you can keep in mind there are 3 different techniques available to do this transformation. That means making the data and instructions available in cache memory that is also present in primary memory. That means we are keeping a copy of the data and instructions which are heavily used by the CPU, which are localized to a few memory locations in cache memory. And this mapping process can be done in 3 different ways. One is called associative mapping. The second method or technique is referred as direct mapping. And the third methodology is referred as set associative mapping. So we can discuss about these three different techniques in the next session.